Welcome to the course on advanced power electronics. So we'll cover today multi-level inverters. Coming to these multi-level inverters, the need, first we have to discuss need for multi-level inverters. The voltage source inverter produces an output voltage or current with the levels of either 0 or plus minus VDC, and they are known as two-level inverter. And to obtain a quality output voltage or current waveform with the minimum amount of current, ripple current, they require high switching frequency along with various pulse width modulation strategies. In high power and high voltage applications, P2 level inverters, however, have some limitations in operating at high frequency, mainly due to switching losses and constraints of device rating. So in many, it may be easier to produce a high power, high voltage inverter with a multi-level structure because of the way in which the device voltage steps are controlled in the structure, and increasing the number of voltage levels in the inverter without requiring higher rating of an individual devices can increase the power rating. The unique structure of multi-level voltage source inverter allows them to reach high voltage with low harmonics without the use of transformers or series connected synchronized switching devices. As the number of voltage levels increases, the harmonic content of the output voltage waveform decreases significantly. So coming to now applications of multi-level inverters. So this multi-level inverter is used in electric vehicle as a main inverter, and this asymmetrical multi-level inverter is used for power system application, as it's shown for many purposes, for reactive power as well as typically for interfacing the renewable energy system. Then coming to this multi-level inverters also used for STATCOM as a fax device for large rating, and this multi-level inverter also use variable frequency or variable speed applications for AC motor drive. So, and the cascade multi-level inverter for power line conditioners. Well, multi-level inverter also used for phase shifting and load balancing, and this multi-level inverter is used for high quality power supply. It's also used for multi-level inverters for fuel cells, and multi-level inverters are also used for photovoltaic applications. And multi-level inverter also used in cement industry for large rating drives, and multi-level for mining industry, again for large rating and low speed drive. And multi-level inverter used also for HVDC systems, and multi-level inverters also used for reactive power compensator, typically flying capacitor based 5-level single phase converter as a reactive power compensator, and is typically as bridge inverter for a typical application is 5-level cascaded edge bridge inverter, and the one typical cell for this edge bridge. It's also many applications. It's also used by very philosophically called the roving cone drive, in which we use. So on input side we have a multi-pulse converter giving isolated DC, and then we use the inverter, hybrid inverter in series, so that number of levels are increased, and you can reduce the switching frequency. You can go for high power. Now coming to concept of multi-level inverter. On the multi-level inverter, you can see just typically one leg of inverter with 2 levels, and then the 3 levels with the 2 capacitor midpoint, and the n levels if you have a number of capacitors like here, and you can increase the number of level in the output from starting to 0 to different we added into that. So now this multi-level inverter includes an array of powered semiconductors and capacitor voltage sources, the output of which generate voltage with the stepped waveform. And output voltage of multi-level inverters are the sum of voltage due to the combination of the switches. And a 2-level inverter, as shown in figure, generate an output voltage with the 2 level with respect to the negative terminal of the capacitor. And the 3-level inverter shown in figure B generate the 3-level voltage, and n-level inverter shown figure C generate typically level voltage. Thus, the output voltages of multi-level inverters have several levels. And considering the m number of the steps of the phase voltage with respect to the negative terminal of the inverter, then the number of steps in the voltage between the two phases of the load K equal to 2m plus 1, where the number of steps P in phase voltage of the 3-phase load in star connection is P equal to 2K minus 1. And by increasing the number of levels in the inverter, the output voltage have a more steps, generating a staircase waveform which have a reduced harmonic distortion. And these are typically a case of series connected capacitors constitute the energy tank for inverter, providing some nodes to which the multi-level inverter can be connected, and each capacitor have same voltage EM, which is given by EM equal to VDC divided by M minus 1, where M is the number of levels, like, and the typically output voltage of a 5-level multi-level inverter, and you can just see this line voltage is closer to sine wave, which is shown by the dotted. So you can see only the difference between the two. Like, now the general structure of multi-level converter is to synthesize a nearly sinusoidal voltage from several levels of DC voltage, and typically obtained from capacitor voltage sources, and the output voltage during the positive half cycle can be found from VO equal to N equal to 1 to M En and SFN, and where SFN is the switching or control function of N node, and it takes a value of 0 or 1. So to generate an output voltage with positive and negative values, the circuit topology have another switch to produce the negative part VOB, so that VAB equal to VAO plus VBO equal to VAO minus VBO. Now coming to features of multi-level inverter, they can generate the output voltage with extremely low distortion and low dV by dt, and they can operate with the lower switching frequency. They draw input current with very low distortion, and they generate a smaller common mode voltage, thus reducing the stress in the bearing voltage, motor bearing. In addition, using a sophisticated modulation method, the common mode voltage can be eliminated. Now coming to the classification of multi-level inverters, the multi-level inverters are classified into 3 categories broadly: the diode clamp multi-level inverters, then flying capacitor multi-level inverter, and cascaded multi-level inverters. So coming to this multi-level inverter topology, so you can say first the neutral it's called neutral point clamped inverter, where your midpoint is connected through the diodes and device upper and lower, and the second is cascaded edge bridge. You cascade the several edge bridges in series of each single phase edge bridge is corresponding, and then the flying capacitors typically. So these are the basic fundamental block of these different kind of multi-level inverter with one phase, and you can extend to any number of phases, normally for the 3 or more than 3 for many applications for high power rating. So the diode clamp inverter was also called neutral point clamped NPC inverter when it was first used as a 3-level inverter, in which the midpoint level was defined as a neutral point. A diode clamp in multi-level M level inverter DCM-LI typically consists of M-1 capacitors on the DC bus and produces M level on the phase voltage. So this is typically one leg of the bridge of diode clamp inverter, and this is on the right side is a single phase with typically the 2 legs of this multi-level converter. So in 5-level inverter, for a DC voltage VDC, the voltage across each capacitor is VDC by 4, and each device voltage stress is limited to 1 capacitor voltage level VDC by 4 for through clamping diodes. And M level inverter leg require M-1 capacitor and 2 M-1 switching devices and M-1 into M-2 clamping diode. So this is diode clamp inverter. Typically you can call it the output voltage and switching states of diode clamp voltage level and their switches. Like, so you can just start with typically how we switch off for V5 equal to VDC, then V4 equal to 3 VDC by 4, then V3 equal to VDC by 2, and V2 equal to VDC by 4, and then V1 equal to 0. So now in this 5-level diode clamp inverter, turning on all the switches as SA1 to SA4, VO equal to VD, and turning on the 3 upper switches like SA2 to SA4, and lower switch SA1 produces VO equal to 3 VD by 4, and turning on the upper 2 switches SA1, SA3 to SA4, and 2 lower switch SA1 to SA2 produces VA equal to VDC by 2, and turning on one upper switch SA4 and 3 lower switches SA-1 to SA3 produces VA equal to VD by 2, and turning on all the lower switches SA1 to SA-4 VA equal to 0. Now this is the fundamental and harmonic analysis of 3-level inverter. So you can clearly see how the fundamental varies with your typically the kind of pulse width, and then how the other harmonics are also typically are there, the magnitude, and you can see somewhere depends on the width, typically order of like a 30 to 60 degree you are having a lot of harmonic reduction. Like, so this is a single phase 4-level diode clamp inverter, where you are using typically the capacitors for getting the in between levels, and then you are using a, of course, anti-parallel diode with the devices. Then this is a single phase 5 level diode clamp inverter, and this is the capacitor charging profile. I mean the voltage in the out, typically the output, and how typically the current flowing. I mean with the this your capacitor is charging capacitor charge, and this is a phase and fundamental voltage waveform of a 5 level inverter. So you can see the waveform is closer to typically sine wave, and this is the pendulum switching of 5 level inverter. When the modulating signal is compared with the your carrier and reference waveform, and carrier is your typically you can call it multi level different kind of waveform with the typically at different levels like. And this is typically single phase 6 level diode clamp inverter, and this is the switching scheme of diode clamp 6 level, where it is start V5 start 5 VDC and it goes to like a typically to 0. So you have a level of VDC, 2 VDC, 3 VDC, 4 VDC and 5 VDC in positive as well as in negative direction. And this is a typical line voltage waveform of 6 level diode clamp inverter. So you can see certainly the harmonics are reduced and waveform goes as closer to sine wave as possible. You can clear. And this is single phase 7 level diode clamp inverter, and the TAD level in AC line current with different levels. You can just see as the level increases, it reduces even typically less than 1% if you go higher number of level. But initially there is a drastic reduction up to 6 to 7 level or 8 level. After that, it does not reduce to that much level. So now coming to the features of diode clamp inverter, a high voltage rating for blocking diodes, although each switching device is only required to block a voltage level of VDC by M-1, the clamping diodes need to have different reverse voltage blocking rating, and the blocking voltage of each clamping diode in the diode clamping inverter is dependent on its position in the structure. And in an M level lag, there can be 2 diodes, each seeing a blocking voltage of VD equal to M-1 minus K divided by M-1 into VDC, and where the M is the number of levels, K goes to the 1 to M-2, and VDC is the total DC length voltage. Now on unequal switching device rating, so if the inverter design uses the average duty cycle to find out the device rating, the upper switches may be oversized and the lower switches may be undersized. So if the design uses the worst case condition, then each phase has 2 into M-1 upper devices oversized, and coming to capacitor voltage unbalanced. So because the voltages at the capacitor terminals are different, the current supplied by the capacitors are also different, and when the operating at unity power factor, the discharge time for inverter operation or charging time for rectifier operation for each capacitor is different. Such a capacitor charging profile repeats every half cycle, and the result is unbalanced capacitor voltage between different levels. Now coming to the advantages, when the number of levels is high enough, the harmonic content is low enough, provide the need for filter, and inverter efficiency is high because all the devices are switched at the fundamental frequency and the control method is simple. However, the disadvantage are excessive clamping diodes are required when the number of levels is high, and it is difficult to control the real power flow of your individual converter in multi-converter system. And they typically the improved diode clamp inverter. So here the problem of multiple blocking voltage of the clamping diodes can be addressed by connecting an appropriate number of diodes in series as shown in the figure. And however, due to the mismatches of the diode characteristic, the voltage sharing is not equal. Then improved version is also obtained by using a distributed clamping diodes as shown in the adjoining figure. So now coming to a flying capacitor kind of multi-level inverter. So the above figure shows a typical configuration of 5-level flying capacitor inverter, and it is evolved from the 2-level inverter by adding DC capacitors to the cascade switches, and there are 4 complementary switch pairs in each of the inverter lag. And in flying capacitor solution, the additional voltage step is obtained by the use of separate DC capacitor in each page, and this capacitor is pre-charged to 1/2 of the total DC voltage across the converter bridge, and the total capacitor power rating is considerably larger for this topology than for the 2-level or 3-level neutral clamp topology. The 3-level flying capacitor concept can be extended to provide any number of voltage level by adding further capacitors and dividing subdividing the voltage source converter valve, and the size of the voltage increment between the two capacitors define the size of the voltage steps in the output voltage waveform. And the flying capacitor has great flexibility than the diode clamp converter. So this is typically a single phase 4-level flying capacitor inverter, and this is single phase 5-level flying capacitor inverter, and this is a single phase 6-level flying capacitor multi-level inverter. So you got this idea. Flying capacitor 6-level inverter redundant voltage level and corresponding switch states are shown here. So you get the voltage starting from typically like 5 VDC to coming to your VDC, or typically the kind of 0. And this is the different switching pattern. So flying capacitor 6-level redundant voltage and corresponding switching state. And this is by a 6-level inverter redundant and corresponding switching state. And this is your flying capacitor 6-level inverter with the corresponding switch state. And this is the single phase 7-level flying capacitor inverter. So coming to large number of features of flying capacitor inverter, the large number of capacitors, the inverter require a large number of storage capacitors. Assuming that the voltage rating of each capacitor is the same as that of a switching device, and M-level inverter converter requires a total of M-1 into M-2 divided by 2 auxiliary capacitors per phase. And lag in addition to M-1 means DC bus capacitor. So now coming to balancing capacitor voltage, so unlike the diode clamp inverter, the flying capacitor inverter have redundancy at its inner voltage level, and the availability of voltage redundancy allows controlling the individual capacitor voltage, and in producing the same output voltage, the inverter can involve different combination of capacitor, allowing preferential charging or discharging of individual capacitor. So now coming to the advantage of this flying capacitor multi-level inverter, so large amount of storage capacitor can provide the capability during the power outages, and these inverter provide switch combination redundancy for balancing different voltage levels. And like the diode clamp inverter with more level, the harmonic content is low enough to avoid the need for filters, and both real and reactive power can be controlled. The disadvantage is an excessive number of storage capacitor is required when the number of levels is high, and the inverter control can be very complicated, and the switching frequency and switching losses are high for real power transmission. So now coming to cascaded multi-level inverter, the one multi-level converter topology incorporate cascaded single-phase edge bridges with separate DC sources, and this comment makes relevant energy sources such as fuel cell or photovoltaic natural choice for the isolated DC voltage source needed for cascaded inverter. The AC output of each of different full bridge inverter levels are connected in series such that the synthesized waveform is the sum of inverter output. And these are typically an example of your single phase multi-level cascade edge bridge inverter, where you have a typically your M-1 kind of bridges. So the number of the output phase voltage in M levels M in cascade inverter defined by M equal to 2S plus 1, where I see the number of separate DC sources, and the conducting angle θ1, θ2 to θn can be chosen such that the voltage total harmonic resistance is minimum, and normally these angles are chosen so as to cancel the predominant lower frequency harmonic. And for the 11 level case, the 5th, 7th, 11th, 13th harmonic can be eliminated with the appropriate choice of your conducting angles. And one of the main advantage of the cascade inverter is that the series of edge bridge makes the modularized layout and packaging, and this enables the manufacturing process to be done more quickly and inexpensively. So also the redundant voltage levels can be included in an application design so that the inverter can still operate even with the loss of one level, and this enables the multi-level inverter to continue to function even when there is a problem with one of the DC sources or with one of the power electronic devices that makes up the edge bridge. So both the line-to-line voltage and currents are almost sinusoidal without use of any output filter, and electromagnetic interference and common mode voltage are also inherently less because of the low switching frequency and low dV by dt, that is 21 times than the 2 cascade, and sinusoidal output voltage. The combination of multi-level steps and pendulum enables a great deal of flexibility in the desired output waveform. A pulse rotation technique similar to The one used for fundamental frequency switching of cascade inverters can be used when a pendulum output voltage waveform is desired, and which is the case of at low modulation indices. The effect is that the output waveform can have a high switching frequency, but the individual levels can still switch at a constant switching frequency of fundamental frequency if needed. So now coming to three-phase topology. So this is a three-phase, three-level diode clamp inverter, and the is corresponding pendulum switching for three-phase, three-level inverter, and this is the line voltage in the three-level inverter, and this is the phase voltage of three-level inverter, and this is the three-phase, four-level diode clamp inverter, and this is the device switching status for four-level inverter, where the device switching and inverter output voltage profile is there, and this is the three-phase, five-level diode clamp inverter, and device voltage status of five-level inverters, the device switching and the inverter phase voltage, and this is the three-phase, six-level diode clamp inverter, and this is the diode clamp six-level inverter voltage level and corresponding switch states from typically from 5 VDC to 0 and then minus 0 to minus 5 VDC. This is the line voltage waveform of six-level diode clamp inverter. As you can see how close is the with the fundamental, and this is the three-phase, seven-level diode clamp inverter. And then how the number of switches with the number of level increase. So number of level, if you increase M, you can see the number of switches increases in your existing 2 into M1, and in case of modular it comes N equal to M plus 3 with the red digits on there, or going to be even high level up to 33 or 1. So this three-phase, three-level flying capacitor inverter, and the three-phase, four-level flying capacitor inverter. This is a modulation scheme for output of a four-level multi-level inverter. How the typically the output voltage waveform, how the switching, and how the harmonic spectrum for level multi-level inverter. So you can clearly see typically the case how the harmonic analysis is there. This is three-phase, five-level flying capacitor inverter, and this is the typical level shifted pendulum for five-level converter. This is the three-phase, six-level flying capacitor inverter, and this is the three-phase, six, seven-level flying capacitor inverter. This is your level shifted pendulum for seven-level converter, and this is your now cascaded inverter topology for five-level cascaded inverter, but no switching device is in series. And this is the output voltage and switching status for five-level inverter topology. So these are typically waveform N composed of five-level 2E, 3, 0, minus E, and 2E. And this is your seven-level single-phase, seven-level cascaded inverter. And this is typically cascaded inverter topology with the 9-level, and this is the 9-level cascaded inverter topology with the circuit as well as output waveform of 9-level phase voltage. And this is the inverter modulation scheme with the bipolar modulation. So bipolar VAB equal to minus VDC plus VDC, and or plus VD to minus VD, as you can see in the waveform. And this is a bipolar modulation harmonic spectrum. How it goes in HB inverter. Going to bipolar modulation harmonic spectrum, the fundamental voltage increases linearly with the modulation index, and the dominant harmonic MF has the high magnitude VC is even higher than the fundamental for modulation index higher than 0.8, and this harmonic along with the side bit can be emulated by the unipolar pulse width modulation scheme. And this is the typically unipolar modulation scheme with the two modulation wave VM equal to VM and VM minus, and over carrier wave VCR, and unipolar VAB from 0 to plus PD and or 0 to minus PD, and you can see the harmonic content in that. So usually the unipolar modulation normally requires two sinusoidal modulating wave VM and VM minus 1, which are the same magnitude and frequency but 180 degree out of phase. So these two modulating signals are compared with the triangular to generate the gating pulses. So two upper switches do not switch simultaneously, typically where the all four devices switch at the same time, and the two lower order harmonics generated by the bipolar such MF equal MF and MF plus minus are eliminated by unipolar switching. So the unipolar modulation can also be implemented by using only one modulating wave VM but two phase shifted carrier wave VCR and VCR minus, and these two carrier wave has same frequency and amplitude but 180 degree out of phase. And you can say how the unipolar modulation, the modulating wave and two carrier wave of VCR and VR in this, and you can see clearly how unipolar output voltage is available, either plus VD or minus VD. The three-phase 3-level cascaded inverter, and the 3-phase 7-level cascaded inverter. This is your two unequal DC voltages with E2E 2-level cell or E3A. That is called, this is called binary. This is called ternary level 9-level topology. With the two edge bridges give the 9 level, and then we have a typically 2-cell 7-level topology with the E2E, and this is the switching unequal voltage 2-cell 7-level topology with the switching state as well as the typically the output. So now coming to advantages of edge bridge inverter. So device voltage sharing is automatic because of the independent DC supply, and there is no restrictions on switching pattern. So with the N devices in bracket each capable of operating at voltage E per phase, the circuit can produce an output varying between plus minus N by 2 into E by 2. This is the same as the series device solution. The advantage is that the output has many more levels, giving a smaller voltage step to the load and less harmonic distortion for a given switching frequency. And each disadvantage, each edge bridge needs a isolated DC supply compared to the other solution which need only one supply. Normally this requires some sort of complicated transformer arrangement. Also the capacitor associated with each each supply can be large. Now coming to carrier-based PWM technique. So the carrier-based modulation schemes for the multi-level inverter can be generalized, classified as phase-shifted modulation, level-shifted modulation, and both schemes can be applied to the CHB inverters. Now coming to phase-shifted PWM. So for this type of modulation, a multi-level inverter with M level requires M-1 triangle carriers, and all triangular carriers have the same frequency and same peak-to-peak amplitude, but there is a phase shift between the any two adjacent carrier wave given by 360 by M-1, and this is the phase shifted PWM for 7-level inverter. So number of levels M equal to 7, phase shifted 360 by MC, that is 60, number of carrier wave MC equal to 6, that is a -5. The carriers for H1 bridge is VCR and VCR are minus, and carrier for H2 is VCR2 and VCR CR2 minus 2, and carrier wave for H3 VCR3 and VCR3 minus, and M equal to 7. And these inverter waveforms are well shifted. So switching occurs at different frequencies. So I have switching equal to 60 MF, that is 600. Inverter phase voltage level 7, low electromagnetic current, line to line voltage level is 17, and close to sinusoidal low TAD. And this is the harmonic spectrum 7-level phase shifted PWM. So lowest harmonics around 2 MF and lowest harmonics around 6 MF, containing triplet harmonics, and no triplet harmonics equivalent to F sub 2, that is 60 into 6F, or typically 3006F. Now coming to harmonic contains 7-level phase shifted PWM inverter. So you can clearly see how the harmonics are with the modulation index are changing for in this output. So now coming to level shifted PWM and M level inverter using a level shifted multi-carrier modulation requires M-1 triangular carrier, all having the same frequency and amplitude. The M1 triangular carrier is particularly disposed such that the bands take of I are contiguous, and the frequency modulation index is given by MF equal to FCR upon FM, which remains the same as that of for the phase shifted modulation scheme, where the amplitude modulation index is defined as M equal to VM upon in bracket VCR into M-1. And this is the typically level shifted multi-carrier modulation for pi level. So number of voltage level is pi, number of carriers are MC equal to M-1 4, and IPD provides the best harmonic profile, as you can see. So coming to level shifted multi-carrier 4/7 modulation 4/7 level. So number of voltage, as you can see the waveform, number of levels M equal to 7, number of carriers are MC equal to M-1 6, and F switching device not equal to FCR and not the same as for all devices. Devices conduction ending in not equal and necessary to swap switching pattern. And this inverter output logic for 7 level, as you can see here. So M equal to 7, so switching occurs at different times, and F switching equal to FCR divided by MC, that is 600, and VAB close to sinusoidal, and low TAD and low EMI, and F switching equal to FC equal to 3600, and TAD reduces to typically here your phase voltage about 18.6 and line voltage 10.8%. And this is the measured for IPD 7 level. So how is the inverter phase voltage, how is the line to line inverter voltage. And this is a level shifted pendulum prototype at Ryerson 7 level cascaded edge bridge inverter. So coming to comparison between level shifted and phase shifted pendulum, so we have a phase shifted pendulum and level shifted pendulum. Both the device switching frequency same for all devices, different for all devices, and device conduction period is same for all devices. However, it is in level is different, and the rotating of the switching pattern no required, but required in case of level shifted. The TAD of the inverter output line to line voltage is good, and level shifted is better, and low order harmonics are no, and very low amplitude with of lower typical low order harmonics. And now coming to pendulum scheme comparison, so you have pendulum at the low MA equal to 0.2, and the phase shifted of TAD of 97.6%, level shifted is TAD is 48.8%. As you can see, the waveform of the TAD are there. So now total harmonic distortion and switching frequency of 600, the 7 level. So you have phase shifted and you have level shifted, how the total harmonic distortion of the output is varying. And this is the comparison of the component requirement for lag of 3-level multi-level inverter for diode clamp, Planck capacitor, cascade. The main switches are M-1 into 2 for all three, and main diodes are M-1 into 2, M-1, 2, and -2 for all converter, and clamping diode M-1 into M-2 and 0, and the DC bus capacitors M-1, there is also M-1 and M-1 by 2, and balancing capacitor 0. And for Planck capacitor, it is M-1 into M-2 by 2. And these are the switching devices, assuming that the load inductance is sufficiently large and the capacitors maintain their voltage so that the output current is sinusoidal, as given by I0 equal to Im sin omega t minus pi, where Im is the peak value of the load current and pi is the load impedance angle. So coming to switching device current, each input node current can be expressed as a function of the switching function Sfn, as given by In equal to Sfn into I0 for n equal to 1 to m, because the single pole multi-throw switch multi-level inverter zone is always connected to one or only one input node at every instant. The output load current be down from the one or only one input node, that is I0 equal to n equal to 1 to m In, and the RMS value of each current will be typically IU RMS equal to n to m In square divided by in RMS, like. So the coming to I n RMS is the RMS current of the nth node given by n RMS under root 1 upon 2 pi 0 2 pi Sfn I square d omega t for n equal to 1 to m. And for balance switching with respect to the ground level, we get I1 square equal to I5 square and I2 square equal to I4 square. And the voltage balance, coming to DC capacitor voltage balancing. So the voltage balancing of a capacitor acting as an energy tank is very important for the multi-level inverters to work satisfactorily. So you can just see clearly how your balancing of voltage give the kind of waveform. So schematic of 3-level high bridge and distribution of load current. Now coming to average value of input node current I1 given as I1 average equal to 1 upon 2 pi alpha 2 pi minus alpha 2 pi 0 d omega t, and then we go on at the getting this after solution Im upon pi cos phi into cos alpha 2. So similarly, average value of input current node current I2 is given by I2 average equal to 1 by 2 alpha 1 to alpha 2 I0 d omega t equal to 1 upon 2 pi alpha 1 to alpha 2. Typically, and this is we get similarly average delta node 2 I average equal to 1 upon 2 pi alpha on 2 1 upon 2 pi alpha on 2 I am sin omega t minus pi into d omega t equal to I am upon pi cos phi in bracket cos alpha 1 minus cos alpha 2. So by symmetry I3 average equal to 0, I4 equal to minus I2 average, and I5 average equal to minus I1 average. Thus the each capacitor voltage should be regulated so that each capacitor supply the average current per cycle as follows. So IC1 average equal to I1 average equal to IM upon pi cos phi cos alpha 2, and IC2 average equal to I1 average plus I2 average equal to IM upon pi cos phi into cos alpha 1. So therefore IC1 average is less than IC2 average for alpha 1 less than alpha 2, and this results in capacitor charge unbalancing and more charge flows from the capacitor C2 or C3 than that of outer capacitor C1 or C4. So the equation can be extended for n capacitor for multi-level converter given by ICN average equal to IM upon pi into cos phi cos alpha n, and where hence cos alpha 1 and cos alpha 2 equal to IC2 average divided by IC1 average. So which can be generalized for n minus 1 capacitors. So cos alpha n divided by cos alpha minus 1 equal to ICN average divided by ICN minus 1 average. So which means that the capacitor charge balancing exists regardless of the load condition, and it depends on the control issues such as alpha 1, alpha 2 up to alpha n. Now coming to numerical problems. So numerical examples. So example 1, a single phase cascaded bridge inverter uses unequal DC source of V1 DC equal to 100, V2 DC 50, and then V3 DC equal to 25. To determine the total number of voltage level, and second is capacitors of peak output voltage. So solution is the total number of levels in n H bridge cells with unequal sources is levels equal to 2 n plus 1, and for substituting n equal to 3, so some levels are 2 to the power 3 plus 1 equal to 9. And the peak voltage is the sum of all the voltage sources. So V peak equal to V1 DC plus V2 DC V3 DC, and that comes typically 175 volts. So coming to example 2, a single phase diode clamped inverter has M equal to 7. Find the peak voltage rating of diodes and switching devices if VD is equal to 5 kilowatt and I0 equal to your 50 sin theta minus pi by 3. So coming to solution for a diode clamp inverter with M level, the voltage across the switching device is Vp equal to VDC by M minus 1, and putting a value it comes to 33.3 volt. The diode will have two different ratings for given expression, Vd equal to M minus 1 minus K divided by M minus 1 into VDC, so where K goes from 1 to M minus 2, and has the different voltage. Diode rating will be Vd1 equal to, putting a value it comes for 117 kilo ohm, Vd2 and putting value equal to, that's a 3.33 kV, and VD3 it comes 2.5 kV, VD4 comes 1.67 kilovolt, and VD5 comes 833.3 volt. Now coming to example 3, for a cascaded inverter for M equal to 6 including 0 level, to find the generalized Fourier series of the phase voltage, find the switching angle to eliminate the 5th, 7th, 11th and 13th harmony if the peak fundamental voltage is 80% of its maximum value. So for the cascaded inverter M levels including 0 level per half phase, the output voltage per lag is Vn equal to Va1 plus Va2 plus Va3 equal to Vm minus 1, and due to the quarter symmetry along with the x-axis, both Fourier coefficient A0 and R0, but Vn is for VDC by pi in bracket alpha 1 pi by 2 sin n omega t into d omega t plus alpha 2 pi by 2 sin n omega t into d omega t plus alpha m minus 1 2 pi by 2, that is sin n omega t into d omega 2. So now coming to simplifying, Bn equal to 4 VDC upon n pi in bracket j equal to 1 to m minus 1 cos n alpha j, and which give the instance phase voltage Vn equal to Vn equal to 4 VDC by n pi in bracket your summation is j equal to 1 to m minus 1 cos n alpha j into sin n omega t. So if the peak output voltage Vn must be equal to the carrier phase voltage, so we CR peak equal to M minus 1 VDC, thus the modulation index becomes M equal to VCR peak upon Vn peak, so VCR peak divided by M minus 1 into VDC. So now come to eliminate the 5th, 7th, 11th and 13th harmonic provided the peak phase voltage 80% and its maximum value, and the following equation must be solved for M index M equal to 0.8. So putting typically the different equation of cos phi alpha 1 plus cos alpha 2 cos alpha 5 alpha 3 cos alpha 5 alpha 4 cos alpha equal to 0, cos 7 alpha. So similarly for 7th harmonic, 11th harmonic, 13th harmonic equal to 0, and for cos alpha 1 plus cos alpha 2 plus cos alpha 3 cos alpha 5 plus 4 plus cos alpha 5 equal to m minus 1 into m, or equal to 5 into 0.84. So these can be solved iteratively to find out the angle. So alpha 1 comes to, after solution, 6.57 degree, alpha 2 18.94 degree, alpha 3 27.18 degree, alpha 4 equal to 45.18 degree, and alpha 5 equal to 62.24 degree. So coming to example 4, compare the number of diodes and capacitors for diode clamp, flying capacitors, and cascade inverter for m equal to 9. So coming to solution, diode clamp inverter, main number of main devices 2 into m minus 1, so it comes here 16. Number of clamping diodes m minus 1 into m minus 2, that is 56, and number of DC bus capacitor m minus 1 equal to 8, and number of balance capacitor 0. So now coming to typically for the case of flying capacitor, the number of main diodes 2 into m minus 1, it comes 16, and number of clamping diode 0, number of DC bus capacitor equal to m minus 1, that is 8, and number of balancing capacitor m minus 1 into m minus 2 divided by 2, that is equal to 28. And cascade inverter case, so number of main devices 2 into m minus 1, that is 16, number of clamping diode 0, number of DC bus capacitors m minus 1 divided by 2, 4, and number of balancing capacitor 0. Now coming to example 5, a 3-phase 3-level voltage source inverter is fed from a DC source VDC, and the required output RMS voltage is 440 volt. The modulus index for the sine pendulum control is 0.9. Find the value of DC bus voltage. So coming to solution, for n level VSI controlled by sine wave pendulum, the output RMS line voltage is given by VAB equal to 0.5 VDC into root 3 by root 2 into m into equal to small n minus 1, and it becomes 0 equal to 0.612 m in bracket n minus 1 VDC. So putting the value in this, so it comes VDC comes 399.42, and I have to get the line voltage of 440. The DC link voltage required is 400. So coming to example 6, in the previous example, if the same line voltage is to be achieved using a 2-level voltage source inverter operated by first a sine wave pendulum, second the space spectrum modulation pendulum, what is the DC link voltage required in each case? Consider the modulus index of 2.9. So using a standard modulation, the RMS line voltage is VAB equal to 0.5 VDC into root 3 by 2 into m, and it by coming to 0.612 m into VDC. So putting the value in the VDC formula, it gives the VDC equal to 798.84. Hence the DC voltage required for central pendulum operated 2-level VSI to get the required line voltage approximately 800, and using a sense or space spectrum model in the RMS line voltage VAB equal to 0.577 VDC into root 3 by 2 into m, that is 0.700 m VDC. So putting value into the formula of VDC, that gives the VDC equal to 619.5 volt. So hence the DC link voltage required for central pendulum operated 2-level VSI to get the required line voltage approximately 700 volt. Now coming to example 7, a 3-phase 3-level VSI designed to feed 15 kilowatt 3-phase induction motor type from 254 volt per phase 50 Hz 3-phase AC means with a central sine wave voltage. To calculate the value of AC line inductor to limit the fifth harmonic component of current to 5% of the fundamental line current. Coming to solution, so value of RMS AC line current given IS1 equal to PL upon root 3BL. Putting a value, it comes 19.69 ampere. The fifth harmonic current to be limited 5% of fundamental current. I5 equal to 0.05 into 19.69, that comes 0.985 ampere. And the impedance to be offered for fifth harmonic L equal to V upon N square IN, or putting a value, it comes 10.315 ohm. And has the value of line AC inductor is L equal to, putting a value in the formula, so it comes 32.823 millihenry. Now coming to example 8, a 3-phase 3-level VSI is required to feed 25 kilowatt power to the 3-phase load at 250 volt per phase, 50 Hz 3-phase AC supply, and the central wave voltage. Calculate the value of AC side inductor to limit the fifth harmonic current to the 4% of the fundamental line current. Also calculate the voltage TFT considering up to 7th harmonic. The value of RMS AC current is given IS1 equal to PL upon root 3BL. So it comes like 32.823 804 ampere, and the fifth armature current is to limit 5% of the fundamental AC current, so that is I5 into 0.04 into 32.04 equal to 1.312 ampere, and the impedance to be offered for fifth harmonic current is XL equal to V upon N square IN, and that is the 7.744 ohm, and the value of AC line inductor are typically L equal to X, typically the reactor divided by the frequency, so it comes 24.65, and the voltage drop due to the inductance is given VLF equal to XL into IL1, so it comes to 254.03 volt. And the converter voltage is calculated V converter equal to VS square plus VL square, so putting value it comes 359.23 volt, and the value of nth harmonics is given Vn equal to V converter upon N, and V5 equal to V converter 5, so it becomes 27.63, and V7 equal to V converter by 7, that is 51.23, so TAD is V5 square plus V7 square divided by converter square, so it comes 16.2%. Like coming to example 9, a 3-level inverter operates with DC voltage of VDC equal to 400 volt. The inverter drive an RL load with R equal to 15 ohm, L equal to 50 millihenry. The output voltage frequency is 50 Hz. To calculate the phase angle phi of the load, determine the power factor of the inverter, and if the inverter is controlled using a staircase pendulum, calculate the peak fundamental phase voltage for the modulation inductor 0.8. So coming to solution, the load impedance Z is given Z equal to under root R square plus 2 pi FL square, or Z equal to, putting a value, it comes 21.71 ohm, and phi equal to tan inverse omega L upon R, that comes 46.32 degree, and has the power factor of circuit cos phi equal to 0.69. And for fundamental switching using a staircase modulation, the modulation index M equal to Vn1 divided by B into 4 VDC by pi. So B is the number of positive steps equal to 1 for the 3-level inverter. By putting the value, the peak fundamental phase voltage given Vn1 equal to 0.8 into 1 into 4 into 4 divided by pi, that is 407.44 volt. Now coming to example 10, in a 3-phase 7-level, all harmonics up to 7th harmonics are to be eliminated through use of 3 single-phase edge bridge. Voltage source converted from the DC source of 780 volt with 75 kilowatt power, and their AC terminals are connected to a series cascaded isolation transformer. If it is connected to the 3-phase AC means of 40 volt, 50 Hz, calculate the transformer turns. Also consider the modulation index to be of 0.95. So for hysteresis modulation based cascade inverter, the modulation index is given as M equal to Vn1 divided by B into 4 base upon pi. So for MA is the modulation, Vn1 the peak of fundamental voltage, B is the number of bridges cell, and S is the number of per step voltage of 7-level inverter. The edge bridge VSI cells per phase are required to produce 7-level, and hence the peak fundamental voltage given by Vn1 equal to Ma into 4 base upon pi, that is 3.629 S volt, and root mean square value of the phase voltage Vn RMS Vn upon root 2, that is 2.566. The RMS voltage of the inverter fundamental voltage Vn will be equal to Pg equal to 440 by 3, 254, and thus S gives the 254 by 2.556, that is 98.99 volt. In order to get 7-level phase voltage, the step voltage of the cascade inverter equal to 98.99, the DC voltage given 780 volt, and from this one can observe that the transformer T1 should be have a primary winding voltage equal to 780 volt, and the secondary winding voltage to be equal to 98.99 volt, and the turns ratio of the transformer T1 is given N1 upon N2 equal to 780 upon 98.99. So these are the references which are used for developing this lecture, and thank you.